let's settle down and let's get ready for class. Oh, hi. All right, very good. Okay, so yes, assignments are being worked on. I guess before we get started, I just wanted to have us kind of a kind of brief discussion with everybody. It's a new world order. And it's a new world order because of something called ChatGPT. And that's okay, you know, the world changes. Things don't stay the same, and there's new technologies, you know. I don't have to use log tables anymore to calculate the slide rule. Well, there you go, right? And, you know, I mean, you got Mathematica, you got all this stuff. I think we're all in this together as a society, trying to figure out, you know, how do we use these tools in AI to help us be better people and do better things in the world. But in the education world, this is something that's a challenge for us in the education field. That's me. And, you know, the degree to which, yeah, so look, let me back up. When the very first lecture, I had a little discussion like, you know, I know all the solutions to my homework are out there somewhere. If you want, you know, if you want to use them, that's up to you. You know, you're an advanced graduate student, you're remembering things. At the end of the day, if you just copy the homework, forget it, you're out of the course. I don't want, you know, that's not the point. But now there's a whole nother layer of this with, oh, you could just even put, you know, Deutsch's quantum optics homework into ChatGPT and it'll spit out an answer. It's pretty damn good. It's kind of scary. God, you know, these models are getting amazing. And okay, what the heck should we do about that? Again, this is very new. This is really, I think, in the last year, you know, these models have become so substantially good. It's amazing what you can do with it. And again, I think it'll be a challenge, I mean, for all of us in the world to figure out how to use these tools for the betterment of the world. I think that's the point, or it should be in my view. But in the class, again, the point I want to make is if you want to use these tools to give you clues, to help you figure things out, they're there. You should. I'm not going to police that, and I don't want. It's not necessarily a bad thing for people to using these tools and AI to help them to understand things better. But if you're just taking the AI solution and handing it in, we can tell. And that's not acceptable, okay? It's not acceptable in the sense, it's also not in your interest. It'll not be the point. Fine, you'll get an A+ in quantum optics. Who cares? No one will care. The point of this course is not that. It's so that you learn to become PhDs in your fields. So, one little pep talk for you, okay? Again, we're in this together. I really feel that way. I do my very best to share my knowledge as best I can with you to, you know, transfer knowledge. I've been at this for a while, longer than you guys, and I want to help to share my knowledge as best I can and to give you tools to help you develop your own understanding, to make it your own, so that you have your own way, so that you will say, I'm not going to use Deutsch's notes when I teach one. I'm going to write my own notes because I have my own way of thinking about it. The same way, I don't want to use some Scully textbook. Forget it. I know how to do this my own way, and I want you guys to do the same. And the only way is if you do it yourself. If you don't do it yourself, you're not learning anything. And so don't bother, okay? So that's all I'm gonna say about this. And if you know anything you want to discuss with me, I'm happy to. You know, I know the homework sometimes I say, oh God, you know, they got this typo, whatever. Again, this is real life, okay? You know, look at all my imperfections. But again, I just want to emphasize the point that how much I really want to be there to help you, not to be the overseer of you, and I'm doing my best to help you by giving you what I think is the best tools to help you grow. And if you don't want to use those tools, that's up to you. That's your choice. But don't just try to put in an AI copied solution to your homework. That's just not, it's just useless, okay? Yes?
Out of curiosity, is there a specific event or something spawned?
Yeah, the TAs, the last homework assignment, the TAs were, you know, they're doing their best of grading the homework and looking at them and saying, this is clearly, you know, an AI solution. So like, oh God, this is where we're at now in this. Yeah. But, you know, this is a bigger conversation, obviously. I'm sure it must affect you in thinking about your own lives and where you're going to be and what, you know, the things that you do and how this is going to be disruptive for your futures, whether that's your careers, whatnot. And I think I don't have any pearls of wisdom about that because it's as new for me as it is for you. And I think as I say, we'll have to figure this out together. How and what the, you know, for example, things change. Like for example, I used to give take-home exams in my core courses. I stopped doing that because it became useless because everything that's worth doing has been done. And you know, you can find the solution on the web somewhere. And so I, you know, tortured these poor folks with in-class exams in E&M last semester, and you know, and then you know, you don't have enough time, and it was not my favorite way of doing that. So it's a question I am going to have to face about how to, you know, there is a role still, evaluation. Yes, we're in it together. Yes, I want to do my best help of it. Yes, I'm also evaluating and help, and it's an important tool because, well, we need that we need motivators, we need positive and negative feedback to be better and to get in, and ultimately it's also about resources. There's a finite number of positions, there's a finite number, and it's a competitive world. I mean, dog eat dog, that's life too. And so part of my job is also to evaluate how I'm going to do that, and how we faculty are going to do that in a way that's fair to you, and you know, deals with the current realities is a question that we're going to have to grapple with. I wish I didn't have to, but it's just how it is. All right.
We could have an 8-hour exam with catering and everything.
Samir used to have morning exams and he bought us breakfast. It was great.
Okay.
Yeah.
All right. I'm open to suggestions.
Catering.
I have to take dietary restrictions into account. Yeah. Okay. All right. Let's get back into talking about physics. Woohoo! Yay! All right. So, last time we were introducing this notion of the quasi-classical states of a field, okay? We have fields that we measure in the world, and to the degree to which everything at its fundamental level is quantum mechanics. There's some limit or approximate description of the quantum system. This is what we call the classical field, okay? So in particular, we sought states of the electromagnetic field, states in the Hilbert space that describe the quantized field, that we called quasi-classical, and the way we called them quasi-classical is that we sought states such that the expected value of the field operators are the classical fields, okay? And that the fluctuations that we would see in general, this is essentially thinking about the expected value, the mean value of these observables, but not their definite values. They may be fluctuations. If we measure different, after every time we might get a different value, and those fluctuations are what we call quantum fluctuations, okay? And we wanted those to be minimal. And so the states that satisfy that are the states which are where every mode of the field is in a coherent state, okay? So the coherent state is an eigenstate of the annihilation operator, okay? With an eigenvalue that's generally a complex number. That complex number is the complex amplitude classically that we would have of that oscillator mode, okay? And such a state, which the mode would be an eigenstate of the positive frequency component. Remember, the positive frequency components have all the A's, not the A daggers. And so if we just replace every A hat with alpha, we're back to the field. We took the hat off. We put the hat on. I do that every day. Right, okay. And so to deepen our understanding of what these states are, we're just then thinking about this for a single mode. And then we can go back to thinking about the simple harmonic oscillator. The simple harmonic oscillator could describe the mechanical oscillation of a mass, like my arm, or the oscillation of the field, okay? Well, yeah.
Quasi-classical because they're quantized fields that look like our regular classical field.
Right, they have quantum fluctuations, that's why they're quasi, right? So they're not the classical field. The classical field would just have a certain value, and if we measured it, we'd find that value. The quasi-classical states are states that well approximate that. They have a pretty well-defined value of the field, but they might have some uncertainty.
The expectation of these classical, but then you have the fluctuations on top, right?
And you have, and moreover, those fluctuations are not very big, and they become a smaller fraction as the size of the field grows in the macroscopic limit. Okay. Yes.
Does the negative component of the E hat have any meaning?
Let's come back to it. It's a very good question, I'll come back to that in one moment. It's a very good question. But, you know, what is true, let me just quickly say the following. I should maybe remind you of this fact, that if I take the Hermitian conjugate of that, that's the negative frequency component, right? And I'm sorry, this is where this is the complex conjugate A plus. So the coherent states are eigenstates with a bra, right? If I take the bra, we'll come back to the question of does the negative unit have its own eigenvectors? Come back to that in a moment. I'm saying these are eigenvectors, the kets are eigenvectors when I take the Hermitian conjugate. So that's true for the single mode, right? So the single mode, if I look at right, everyone see that this implies that. Okay. Right, so the coherent states of the simple harmonic oscillator are eigenstates of the annihilation operator with eigenvalue alpha. And they have really important and cool properties. If I look at the free evolution of the simple harmonic oscillator, and I look at how does the mean amplitude evolve as a function of time, that's the expected value of A. Remember, A is the complex amplitude, x plus IP, with this particular root 2. And so the mean complex amplitude is the classical solution, whose real and imaginary parts evolve according to the classical trajectory. Yeah?
We're getting the expectation value for that, but it's not on permission, so that means it's not an observable, right?
That's a very, okay, hold that thought. Excellent thought. Put a pin in it. Okay, we'll come back to that. So, this is a complex number. It is what it is. Okay, I'm going to hold that thought. I put a pin in about the notion of observable. Okay. But it's a very interesting question. Okay, so what we were saying is that the mean complex number is this, the two quadratures, and if this were a mechanical oscillator, this would be the position and momentum of the oscillator, of the mass. They evolve according to the classical trajectories, which are the real and imaginary parts of the complex amplitudes, okay? So, check, they satisfy that, and moreover, they satisfy the property that they, at all times, are the minimum uncertainty product. Delta x and delta p at all times is a half, and even more, they have equal amounts. Delta x and delta p are always 1 over root 2, okay? There are other states that always have the minimum uncertainty, but don't have equal uncertainty in x and p. They're called squeeze states. We'll talk about them next semester. I thought I would get to this semester, but we won't. Okay. Right. So, again, we often, it's very useful to think about this in phase space or phasor space. This is the complex amplitude, which is a point in phase space, or equivalently a point in the complex plane, the complex alpha plane, whose real and imaginary parts are the two quadratures. And classically, if I had a state that had a certain energy, it would move with angular velocity omega in the clockwise direction, and that would be the motion, and the x would go back and forth, and p would go back and forth. This state is not an eigenstate of that we have. I can't have a definite x and a definite p. I can have a state that is localized around some point in phase space with some quantum uncertainty. And that quantum uncertainty is technically called the uncertainty bubble, okay? Which is kind of tells me what the one RMS distance, and it's a circle, because at all times the projection is the same, okay?
Formally what it's called, the uncertainty bubble?
Yes.
Cool.
That's what, it's what everyone calls it, so that's what we call it. And so what this means is that if I had a detector that could measure the observable x as a function of time, I'm not going to get the classical trajectory, which is this, but I'm going to get something which it goes around with some noise around.
That's what I have the question. Is that like you take one shot for the time? It's like even
At every time I measure this, but at different time I might get this. At different time I might get that.
So you average, and even in that average.
That's at one time.
Yeah.
In one time. So
One
this
time,
is
many
this.
shots.
In the end, we always have to say within some bandwidth.
Okay.
But so otherwise, I couldn't really talk about a set measure zero. So it's within some detection bandwidth or some detection bin averaging time. But I should think about this first conception, then we'll come back to how I operationally measure it. Is given the state X. Maybe I'll come back to this. There was a space here I was left for a reason. Well, I'll do this next. So now I ask you the following question. I have prepared the oscillator in this state. And I want to know, at a given time, what is the probability that I'll find the value X? Well, I can't say exactly. I can always say the probability density, right? Because this is a continuous variable. We can only talk about, if I wanted to talk about the probability between X and X plus dx, I can talk about that. But if I want to talk about the probability density at a given time, how would I, so what's the probability of finding X at a given time? Given the state that was initially, so at time t equals 0, I have the state. Let's start an easy way. What at time t equals 0, I provide. This is my state. Okay, we'll say at a later time. Okay, so how would I calculate that? How would I find that? Yes.
Project X on the A.
Yep. So I project X onto. It's the probability amplitude squared. Right? Well, that's what you said. I mean, if I thought of that as a projector, that's right. This is what we might call the wave function.
Mod squared.
Okay. So, what you are asked to show for homework, and we'll show how to do it, is that the answer to this is the following. I'll define alpha as having, so this is the eigenvalue, okay? So, and similarly, I'll call this just, that's the probability. The probability of seeing P at time t equals 0. Oh, that's not, yeah. But this is correct. The wave function is a little, has a phase on it, but I'm just asking about the probability. Okay? So what do you notice about this? What kind of probability distribution is that? What is that function called? A normal or a Gaussian distribution. Which is to say, if I were to measure this, I'm going to see on average this value. So the mean value of X is X0, which is what it is. Right? That's X0. And what's the fluctuation in X? Everyone should memorize the form of a normalized Gaussian. Now, back in the day, before the European Union had a unified currency, every nation had its own currency, and I've told this story before. The Deutsch mark, when it was 100 Deutsch mark, had Gauss as, it wasn't Andrew Jackson, it was Gauss, and had the Gaussian on the bill with the normalized form, so you could just whip it out where you needed it, and it was awesome. But then, yeah. Okay, so what is the form of a Gaussian? A Gaussian distribution is one which,
Excuse me?
Bear with cheats.
It's the one system.
Everyone should memorize this. You should know this. A Gaussian distribution is specified by two numbers, its mean and its variance. Its mean is this, and its variance is sigma squared. So given that, what is the variance of this? Yeah, or the RMS, and the variance is a half, right? Because you see that, it's got a 2 sigma squared. So this is as expected and similar. So what that means is if I were to, at t equals 0, if I were to measure this, I would find it was be Gaussian distributed. And it's true at any point. In fact, the general solution, which you will find, is that. Yeah.
You're referring to the standard deviation as the root mean square. I mean, it is.
Yeah, the root mean square is the standard deviation. Those words mean the same thing. Okay? So there's a Gaussian fluctuation in the quadratures. Okay? If you measure the quadrature, which you can do through a Omega measurement, we'll get to that later, next semester, then you would find a Gaussian distribution. Okay? And at every time it's the same Gaussian, but just the center of the wave. And that gap, okay? Now, that picture here, really, we should understand in the mechanical picture, where we're thinking about a mass on a spring rather than the electric field, is that I have a mass moving in a quadratic potential. And what I have, if it was the ground state, would be a Gaussian, but the Gaussian is just oscillating back and forth here. And that Gaussian oscillating back and forth means that X and P are always Gaussian, and the center of the wave packet just moves on the classical trajectory. And the Gaussian's not breathing, it's not spreading, there's no spread in the wave packet. The Gaussian just moves back and forth. That's what this picture is. Now, here's something that is always super duper confusing. This is not the motion of a photon, okay? The X and P here are not the position and momentum of the particle. They are properties of the wave. The wave is a collective, 7 of 9, the Borg. It has many different, it's the collective of all the particles, because in fact, the coherent state is a superposition, it's a wave packet, which is a superposition of the Fock states, and the Fock states represent different number of particles. So there's also, we talked about the momentum of the photon, it's h bar k, that's a different momentum than the momentum, which is the property of the field, not the particles. We'll have to scratch our heads for a little bit more and think about it. It's very confusing. Okay? All right. I'm glad some people get my silly jokes. All right. So, good. So, that's one notion of uncertainty. We have X and P, which are the quadratures. The quadratures are properties of the field, the oscillating field, and those quadratures are not well defined if I'm in a coherent state. It's a wave packet in wave mechanics, but it's a packet of the field amplitudes in the field theory. Okay? Good. Moreover, the coherent state, we can ask about the number of quanta, or the number of photons in the field. Yes, Tristan, do you have a question? No. And that's constant, because in the free field, the mean number of photons is conserved, and could reach with the Hamiltonian. And that, we should always think about n as the square of the amplitude, okay? So that's what we had classically, quantumly, that's what the mean number of photons is. However, the coherent state is not a the coherent state is not a number state. It's not an eigenstate of the number operator. Therefore, there are fluctuations in the number of photons. There is an uncertain number of photons. And the fluctuation, the variance in the photon number, we calculated was alpha squared, which is n, which says that the RMS, the standard deviation, the fluctuation of photons is the square root of the number of photons. And moreover, we can find the full distribution, the probability distribution of number of photons in the mode. We're just talking about one mode right now. And this is what we derived for the coherent state expressed as a superposition of Fock states. These are the probability amplitudes in the superposition, okay? So in general, the coherent state has some amount of the vacuum, some amount of one photon, some amount of two. It doesn't have a definite number of photons. It has an uncertain number of photons. That was critical to having a mean field. If I had a definite number of photons, the mean field was 0, okay? And the probability distribution that we found last lecture, just looking at the square root of that amplitude, is this, which is the Poisson distribution. Now, question came up, I read says, you know, how in the, I mean, what does this have to do with the Poisson process? I mean, it seems it just came out of nowhere, which it did. We didn't put any of the assumptions in any clear way, and we'll talk next lecture about a Poisson process for counting. And if you've studied, I hope you have, some statistics, the notion about a stochastic process and then the probability distributions you have when you have probability just happening as a function of time. And we'll say more about that next week. But I just want to say one thing, and this sort of came up in one of Benny's questions yesterday, last time. So, I mean, if you come back to this expression, what is it saying? It's saying if I apply the annihilation operator to the state, I don't change the state, right? I mean, if I apply the annihilation operator to the one photon state, I've annihilated that photon. It's now a 0 photon state. But if I apply the annihilation operator to the coherent state, it doesn't change the state. I mean, I have to renormalize it because this. So if I were to measure again, I do it again. Now, why is that happening? Well, of course, this thing goes up to infinity. There is some probability amplitude infinity, and when I annihilate it, I brought what was at 1 down to 0, what was at 2 down to 1, and I did it in such a way that I didn't change the relative ratios of any of them. I just changed the overall amplitude, and that's what happened. That's how this came out. That recursion relation is how that came out. So at some level, one thing it says, you know, when in a Poisson process, when you detect, your chance of detecting next is completely uncorrelated. That's what it means to be a Poisson process. And so the coherent state, because of this property, annihilating a photon doesn't affect my chance of detecting in any way the next photon, because it didn't change the statistics in it in any way. That's the essence of why this is related to the Poisson process. Yeah?
Is this comparing annihilating a photon to measuring it?
Yeah, it's a very good point. So that's a whole nother layer. So we typically learn when you do a measurement, after the measurement, if I measure an eigenvector of the system, the post-measurement state, I apply the projection operator associated with the eigenvector of the eigenvalue I was measuring, right? That's the collapse of the wave function. This is a more generalized measurement. If I measure a photon, but I'm not doing a measurement of the number operator, my detector absorbed the photon and it's gone. Then the post-measurement state would be you apply what's called the Krauss operator, which in this case is the annihilation operator, to the state, and then we normalize it. So there is this a more generalized version of how do I update the quantum state conditioned on the measurement I did. It's a form of Bayes' rule. Yeah, I mean, Bayes' rule says I have my priors, I learned something, how do I update the probability distribution? This is a generalization. All right, very good. So, you know, I want to maybe just say a little bit more about, you know, we have another way of when we think about these quantum fluctuations, I want to talk maybe a little bit about complementarity. Okay, so we have, you know, operators that we say are conjugate. X and P are canonically conjugate. Which means we can't write down states that are simultaneous eigenstates of X and P, right? But interestingly, there's this relationship between canonical conjugation and the way in which one observable generates that is to say, X is the generator of momentum translation. And P is the generator of position translation. Well, that last part is obvious. Momentum generates a translation in position. What that formally means, and this is where the computational relations come from, so I can think about, let's say, I'll define T as the operator which translates the system by a distance x naught, okay? To say P is the generator of that is to say this. And what that means is that if I conjugate the position operator and make this unitary transformation, X is translated by X naught. Yes?
So in the definition of a generator, it assumes specifically that form with those exact constants?
Yes.
Yeah.
I mean, the plus and minus depends whether it generates to the right or to the left, but yes. Well, actually, I've gotten rid of H bar, so, but if it had units, it would be over H bar, right? Okay. And the fact that this is true, if I had an infinitesimal translation, gives us this relation. Similarly, I can define M of P naught of e to the plus I P naught X hat, which translates momentum. makes them conjugate variables. I could also act it on the eigenstates of x. If I take the translation operator and I operate on the eigenstate of x, it translates the eigenvector by that amount. That's also true. These are compatible. And similarly, m acting on a momentum eigenstate translates the momentum eigenvector by that amount. Okay. So, very good. So if I think about the coherent state, there's one thing I failed to remember. Coherent state. Firstly, the vacuum is both a Fock state and a coherent state.
Annihilate zero, you get zero.
That's right. So A acting on this, right? And so in this case, it's the state with alpha equals 0. Now it doesn't mean that it doesn't have fluctuations around the mean. If I were to have the vacuum and I were to somehow be able to measure its quadratures, you know, how much I'm measuring, then what I would find is I'm trying to not be periodic, but anyway, it has the same level of fluctuations as the coherent state. The vacuum is that state, right? So the vacuum is a coherent state which it's supposed to be centered at the origin. It has alpha equals 0, but it has fluctuations in x and p. Those are called vacuum fluctuations. Okay? And the level of the fluctuations is the same value that we had before. Okay? Now let's come back to this. Well, if we look at this picture, what we see is that the coherent state is a translation in phase space from the vacuum. If I were to start with the vacuum and I can displace not in either x or p necessarily, but in both x and p, to just displace this state from the origin to being centered at this point in phase space, that should be a coherent state. And so what we want to ask ourselves is, can I have a phase space translation? Or what's called the displacement, phase space displacement operator. Okay? So I want to displace not just in x or in p, I want to displace both in x and p. Now the problem is x and p don't commute. So displacing in x and then in p is different than first displacing in p and then in x. But symmetrize it. Pure. That is genius, right? So I want to think about something which doesn't, because this is both in the exponent, if I were to write this as a Taylor series, minus, sorry, because this guy has plus and this guy has minus, that's what we said before, right? I multiply this out, what you see, I have it's all gonna be all symmetric combinations of x and p. There's not gonna be x's on the left or p on the right. I'm gonna have all the symmetric. So this is what we call symmetric ordering. We'll come back to that next semester. Very important. Okay? Yes?
So, due to these vacuum fluctuations, will that ever manifest as, like, if we have a perfect single photon detector with 0 dark counts, will that ever manifest as detecting a click when a click isn't there? When it's
No, it's a good question. The vacuum is an eigenstate of the number operator. It definitely has 0 photons. So your photodetector is looking for the number of photons. It's never going to see, if I had no dark counts, no thermal fluctuations, it's never going to click. But if I had a detector that didn't count the number of photons, but itself measured the quadrature, I would see. It's a different method. That's a homodyne detector rather than a photon counter. Yeah. Yes?
Did we calculate the RMS for clock states already?
The RMS of what? Of x and p?
For in.
A Fock state has no fluctuations in n. It's an eigenstate of n. But it has fluctuations in x and p.
Okay.
And those fluctuations are n plus a half.
Coherent states do have fluctuations in n, right?
In n. So the coherent state is not a Fock state.
Except for that one.
Except for that one.
Okay.
So this state has a definite number of photons, has no fluctuations in photon number, but it does have fluctuation. Every Fock state has a fluctuation in quadratures, but also fluctuations in n. A Fock state has fluctuations in quadratures, but not in n. The coherent state generally has fluctuations in both. It has fluctuations in the number of photons, and it has fluctuations in the quadratures, except the vacuum. The vacuum definitely has n photons because the fluctuations are the square root of the mean, and the mean is 0. Yes, Nate?
Because that is enough for symmetric ordering,
Yeah.
does that mean the 2 generators commute?
There's not 2 generators here. This is the, I don't have a separate generator of x and p. This is a generator, this is one generator. Let's rewrite this as we often do. So I'm going to write alpha as x naught plus I p naught over root 2. And A as x hat plus I p hat over root 2. Okay, those are my complex amplitudes and annihilation operator. Okay? Then I can substitute in x naught is alpha plus alpha star over root 2 p naught is alpha minus alpha star over I root 2, and similarly x and p, and substitute that in. When you do that, you find that this displacement operator is a function of alpha. Sometimes people write it as also a function of alpha star because there's a whole thing. I should really think about alpha and alpha star as independent variables, but I'm not going to do that. I'm just going to call it that. And when you do that, you find the following. This is the phase space displacement operator, as is very familiar to those who do quantum optics. Okay? This is, of course, I want to remind you that these displacement operators and translation operators, these are unitary operators. Okay? They don't change the normal state, they're just changing the frame. Is this operator a unitary operator? A unitary operator is either the I times a Hermitian operator. Okay. This is clearly unitary because this is Hermitian. Is this thing I times a Hermitian? This is,
A is anti-Hermitian?
it's anti, so e to the a, where a is equal to dagger is minus a, is called anti-Hermitian, which an anti-Hermitian operator is I times a Hermitian operator. So yes, indeed, this is unitary because when I take the dagger of this, I get minus it back, and so that's a. So this u is wrong. Now it's right. Okay. I was gonna say, memorize it. I did clearly. Okay. Yes, sir.
So does alpha kind of represent the translation in the plus n direction, whereas alpha complex would represent like going down?
Go the other direction in my.
So you only go away from the center.
I could alpha. I mean, it depends. So I can go to alpha to minus alpha, and then I was displaced in the other direction. Okay. Before let me just say importantly. So I claim that the coherent state is the phase place displacement of the vacuum. Okay. There's lots of ways to prove that. So, well, graphically, that's how I tried to motivate it. I tried to say, look, this state with the bubble over here is just, I just displaced the vacuum to that point in phase space. And I did it in a symmetric way. That should be the coherent state. Yes, Donald?
Two things. One, so Fock space has 0 RMS. Sorry, not Fock. The vacuum has 0 RMS.
For number.
For number.
Yeah.
And then the other thing was, okay, so D's Hermitian. Can we observe it?
D is not Hermitian.
D is not Hermitian.
D is unitary.
Unitary.
The unitary operator. I'll come back to the question of observables soon. Okay. So firstly, in the same way that I, through a unitary transformation, translate in X or P, if I symmetrically translate X and P, using Baker-Campbell-Hausdorff, this equals that. Okay? So this, remember, this is X plus IP, and the displacement operator is going to displace X to X plus X naught, P to P plus P naught, so it displaces the thing by alpha. So this is an important property of the displacement operator. That's what it means. Okay? Let us check that when I operate the annihilation operator on this, I get back the eigenvalue alpha. Okay? So A acting on the coherent state, I claim is the same thing as A acting on the displacement. Okay. How shall I calculate that?
Bracket.
I could take the commutator. That's perfectly fine, but it's gets a little complicated. The trick of the trade is to use this, which means that I'm going to shove in the identity. This is unitary, which means d dagger d is, oops, d dagger, much better, is the identity. So this becomes d of alpha, d dagger of alpha, a d of alpha acting on the vacuum. But this is a plus alpha. A acting on the vacuum is annihilation. So, and alpha is a constant. Yay. Right?
Checks out.
Very good, that's me. All right, so another way of thinking about the coherent state, it is a phase-space displacement of the vacuum. Okay? Now, I want to show that this also shows the Poisson statistics using some tricks of the trade. This whole putting this together is what is you're going to practice in your current homework is what's called boson algebra. It's the algebra of bosonic modes. It's really the algebra of simple harmonic oscillators. Okay, this is the moral equivalent of the Pauli algebra. That if you're quantum optics, there's kind of two algebras: two-level systems and infinite-dimensional systems. That's kind of all we got. We know everything about Pauli matrices, and we know everything about A and A data, then we're done. All right. All right, so here's an aside. Let's say I have the exponentiation of the sum of two matrices or operators. Then this is equal to e to the a times e to the b times e to the minus a half the commutator of a and b if a commutes with the commutator and b commutes with the commutator. So it truncates at that level. Otherwise, I have multiple commutators. This is a form of what's known of the Baker-Campbell-Hausdorff.
Is that if and only if?
Yeah. Okay. So let's look at my displacement operator, which is e to the, I'll call this A, I'll call this B. Okay. So the commutator of A and B is equal to minus alpha squared times the commutator of A dagger A. Right? Which is what? That's the commutator of A dagger, right? Minus 1.
Well,
Yeah, all right.
it was one, I was.
It's good, it's close. My life is full of minus signs. All right, so that tells me that this guy is equal to e to the alpha A dagger, e to the minus alpha star A, e to the minus a half alpha squared. Okay? So what this is normally ordered. By separating this out, I put all the A's on the right and all the A daggers on the left. Okay? But when I did that, when I commuted through it, I had this form. So now let's act this operator on the vacuum. This is a constant. This is that, and this is that, right? What happens when this acts on the vacuum? The annihilation operator annihilates, reaches 0, and e to the 0 is the identity. Okay? This is the sum over n using the Taylor series, alpha to the n, a dagger to the n, divided by n factorial, acting on the vacuum. You with me? Yeah.
Sorry, why were you missing out that again?
So let's put it back. When the annihilation operator hits the vacuum, I get 0.
I see. Okay.
So the only term that survives is the identity. is that right? This identity plus all powers of the annihilation operator. So this becomes the identity. And if I factor out, wrote it as this, what is this? If I take the creation operator and apply it n times to this divided by that,
That's up.
that's n. And so what we have shown is that the state is equal to e to the minus alpha squared sum over n, alpha to the n over the square root of n factorial n, which is what we have. So this is just another derivation of the same thing. So the coherent state I can think about as the phase space displacement of the vacuum. All right. One last, I was hoping to get to, we'll see what we get. Two last things I wanted to cover, but we'll probably only get to one today. Which is, maybe I'll do it here. When we thought about the classical oscillator, we could say that we had a complex amplitude which had a real and imaginary part, or an amplitude and a phase. Okay? So the coherent state is neither an eigenstate of A or P. The eigenstates of X are like this. The eigenstates of P are like that. Okay? So, and an X eigenstate is a superposition of all the P eigenstates. Well, actually, I'm going to integrate. And a P eigenstate is a superposition of all X eigenstates. So the coherent state was neither an X eigenstate or a P eigenstate. It was some compromise, okay? And because of that compromise, there were quantum fluctuations. The state that has a definite amplitude is a number state. Because the amplitude is fixed, okay? But if we go back over here, we can say, well, how do I define it? What is the conjugate to the amplitude? Or said another way, can I define a state which has not necessarily a well-defined amplitude, but a well-defined phase? Okay. The coherent state, if we look at this bubble again, this coherent state has a kind of uncertainty in phase. It has uncertainty in amplitude, but it also has an uncertainty in phase. So we want to think about how do we define the state that has a well-defined phase, and what is the uncertainty generally in phase when we think about the oscillator? Yes, Don.
When you're talking about amplitude, you're talking about the A.
That's right.
Not the
This is
complex
the
amplitude.
This is the amplitude, and this is the phase.
Okay. So not the complex amplitude, but the amplitude.
Yes. Now, the magnitude of alpha is A. The magnitude squared is A squared. Okay. So, for that purpose, I want to say that N is the generator of translations in phase. That is to say that n, this is a phase space rotation operator. What do I mean by that? Well, let's say that I define the state, I'm going to call it R of theta, is defined to be e to the minus I theta n hat. Right? So let's define that operator. This is a unitary operator. Okay? And I want to know, how does this operator change the quantum value of the complex amplitude? This is like the complex amplitude, but it's the quantized complex amplitude. A is like the complex amplitude. How would I calculate that? The way I do it generally, maybe I should have written this earlier. Even with B, A e to the minus B is equal to A plus the commutator of A with B plus a half the B with A plus B commutator of B with A plus dot 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 1 over n factorial B with A n times.
Would that be B or IB in the e to the B?
This is, I mean, if I write this as B is equal to IH,
Oh, okay.
then this is a general formula. This is a formula associated with the similarity transformation. And if I write B, in this case, B is this. Okay? So this is e to the I theta n hat A, e to the minus I theta n hat. Okay? So if I do that unitary transformation, I have to do these multiple commutators. Okay? And I have to remember the commutator of n with A is equal to minus A, and the commutator of n with A dagger is plus A dagger, which is easy to derive. And when I do that, I get that. Okay? That's coming from this algebra. So notice what this operator did. It took the operator A and it put a phase on it. It translated the complex amplitude by that. This is maybe familiar if I thought about the Hamiltonian as h bar omega A dagger A, which is h bar omega times the number operator. And I look at the time evolution operator, which is e to the minus I over h bar, or e to the minus I omega t n. And I look at the Heisenberg picture, what we've said before. So n generates translations in phase. It takes, if I had a coherent state, it keeps the coherent state the same, it just translates it by that phase. Is that clear? So And that amplitude generates rotations. The rotation is the time translation. In the same way, momentum generates translations in x generates translations in p, and generates translations in phase. Yes?
So just clarify, the reason we're using both the word translation and rotation to describe a similar process is because it is technically a translation in we're translating from
angular
one phase
direction.
to another, but it's a rotation in phase space.
It's a rotation in phase space, but that translates the coordinate phi. Phi goes to phi plus phi naught. Translating the phase corresponds to a rotation in phase space. So the term translation is a translation along that coordinate. Okay? So, by this logic, we should say that the conjugate, in the same way that x was conjugate to p, phase is conjugate to number. Okay? So, we want to try to find out what is the observable that corresponds to the phase. Now, we're not going to get to all of this, but c'est la vie. We've had a good conversation. But let's think about how we define the phase of the complex amplitude. So the complex amplitude has an amplitude and a phase. This is complex amplitude is what I'm calling the M, right? So A is the magnitude of the complex number, which is the square root of alpha star alpha, right? This is the polar decomposition of the complex number. This is to be contrasted with the decomposition in terms of real and imaginary. This is the another decomposition of complex number where x is the real part, where the square root of 2, and p is the imaginary part, with the square root of 2. Now, for when we go to the quantum thing, this becomes the annihilation operator. We can easily define the generalization of the real and imaginary parts as the Hermitian part, and the anti-Hermitian part. What we now seek is the polar decomposition of the operator. That's actually something in linear algebra that we never learned. But we can definitely write it down. If I have a matrix, a D by D matrix, I'll just call it M, with complex entries. I can define this as a unitary times a positive matrix, where the positive matrix is the square root of m dagger m. So if I take the matrix, I multiply it by its dagger, and I take the square root of that. How do you take the square root of a matrix? You take the square root of the matrix by diagonalizing it and taking the square root of its eigenvalues, and that's the square root of the matrix. So this is a perfectly well-defined, and this is a matrix which is positive, which is to say it has no negative eigenvalues. In the same way that the amplitude is a non-negative number, right? And V is M times P inverse, which is unitary, or not V, U. So that means that if I look at U times, say, U dagger U, see I can no, this should be P minus 1, right? Yeah. Or equivalently, U dagger is M P minus 1, P minus 1, and dagger. Now I claim that this object is just like, it's the matrix generalization of the polar decomposition of a complex number. It's a positive thing and a unitary. A unitary is either the I times a Hermitian. So given any matrix, a D by D matrix, I can write down the polar decomposition. So to define the phase operator, I want to do the polar decomposition of the annihilation operator. We're out of time, but I'll just quickly write one thing and we'll pick this up next time. A is equal to V, or yeah, I'll call it V, times the square root of A dagger A. Where, or V times the square root of N. This is the magnitude, and this is what I want to say is like e to the I phase. This operator is the thing that is that, and V is that. When I act A on a number state, I get the square root of n times n minus 1. This guy gives me the square root of n. That's the magnitude. And this thing, I claim, is like a unitary operator. A unitary operator maps a basis to a basis, but notice what this operator does. This is a translation in number. Yeah?
Is the upper bound
Oh, no, it's not. It's infinity. I'm Russian. So we're getting close. If this, in the same way that position translates momentum, momentum translates position, number translates phase, phase translates number. Phase and number are conjugate operate. They're kind of conjugate operators. There's a big caveat to that. I'm hiding something really under the rug. But in the same way that I wrote the states there that had well-defined phases, I can think about these are the states that have well-defined number. They're the energy eigenstates. And these are the states that have well-defined phase. They are the conjugate. The polar coordinates are the conjugate in the same way we had in the Cartesian coordinates. So we'll just conclude to say that the number state had a completely uncertain phase. I don't know the phase at all. The phase states are going to have a completely uncertain number. The coherent state is a compromise. It doesn't have a definite amplitude. It doesn't have a definite phase. If I wanted something that had a well-defined phase, I had to have an uncertainty number. If I wanted to have something that has a certain number, I have to have an uncertainty phase. There's a trade-off in number and phase in the same way that there's a trade-off in quadratures. There's one caveat, and I'll do it. There is no phase on a coherent. It doesn't mean it's not observable. And we'll come back to that next time. In a way. All right. We'll call it quits and let the next class in, and we'll discuss this. I'll take more questions on